So let's begin today's session. Uh, it's been a means like a very good experience with this is the last week. Okay, so thanks to all of you for joining this course. And what we will do today is like we will revise the key takeaway from the subject in terms of means what you should know about radio astronomy. Okay, and after that we will kind of means we will take up half of this session now, and the next I means tomorrow in the live session the next half I will complete. Okay, now what we will do, we will in this session what we will do, I will uh, kind of go through some summary slides, and after that we will have a Q&A session. Okay, so again, hello everyone, I am Harshavinash Tanti and your host here. Okay, so let us revise from the starting. So how this radio astronomy came into picture. Okay, so just a moment. Just a moment. Let's, yeah. So okay. So how this came into picture. So from the earlier means like from the earlier times, what we used to see is some stars and all by naked eyes, so which is in visible range. Okay, this band. Also, we used to see something called twinkling of stars, which is, means in radio astronomy terms, it's also called scintillations. Okay, twinkling or scintillation. Scintillation is just a means like a scientific term which means if your wave is passing through some media, it goes under or means diffraction, which causes twinkling. It can be atmospheric reason, also due to ionosphere. So with this, and in late 1900s, we came to know that besides visible range, there is huge amount of means very broad electromagnetic spectra, and also it was discovered that in radio frequency range, in up to this is I think around 16 megahertz. Okay, to few gigahertz. Okay, about X band till about X band, which is which is 8 to 12 gigahertz around. Okay, for this the atmosphere is kind of transparent. Everything can pass through, and there is nothing as such much of a loss while transmission. So for that reason, people started viewing at this band, and below 16 megahertz band, ionosphere blocks everything. Okay, so we will also see why it does later on, but just here, and also with the kind of also with the knowledge of the radio astronomy and all, we also came to know about something called cosmic wave background and sky temperature means and the flux density and all, for which we tried to build telescopes to see whether all those theories are correct or not. Okay, now the base root of this means the basic theory on which this entire radio astronomy is dependent upon is what is we called the electromagnetics. Okay, so electromagnetics or electrodynamics or EMT means electromagnetic theory. It is made up of two things: electric and magnetic field theories. Okay, and which is nothing but kind of front and back of the same coin, face and tail, head and tail of the same coin. Okay, because and which was uh, explained by Maxwell's equation also. So we had first what electrostatics, something called electrostatics, where we have electric charge, which follows conservation of charge. Then there is something, if we go deep into atomic theories and all, then there is quantization of charge. Or quantization of charge. Why? Because we can have the smallest negative charge as electron, uh, electronic charge. Okay, and then with this came Coulomb's experiment, which gave us Coulomb's law, which is very similar to the gravitational law, which was explained by, which was put forward by Newton, but for electric charges. And here the constant K is nothing but 1 by 4 pi epsilon naught, where epsilon naught is permittivity of free space. Say if there is two charge in a media rather than in a free space, then there is uh, another term which will come into picture, which is ER, which is also called as relative permittivity. Relative permittivity. That means the permittivity of the media to the permittivity of the free space. Okay, this is what relative permittivity is defined as. Okay, and from electric charges comes electric field, then electric field intensities, field lines. There is general rule that electric field lines never cross each other. Okay, and also different concepts like potential. One of the main means main concept which led to explanation of your plane wave. Okay, now potential. What is potential? Potential in general sense means, say, in in terms of literature, potential is ability to do something. Okay, so here also the potential is defined such that if you are doing some amount of work, how much energy will be consumed per minute, means energy will be consumed kind of thing. So that's how potential is also defined. And after this came electrostatics, which was similar to after electrostatics came magnetostatics, which was similar to electrostatics, but this was due to current carrying conductor. Okay, so current carrying conductor will create a magnetic field around it, which will encircle it, and the magnetic field will be directly proportional to the amount of the current in the current element for the small infinitesimal part over the r cube, means the at the distance which you are measuring. Okay, and with this there is a constant term comes k, which is mu naught by 4 pi. Okay, so with all this we moved on to something called electrodynamics, where electric and magnetic field are coupled, and we saw what is plane wave. And that whole thing was governed by something called Maxwell's equation, or the Maxwell's theory put forward by Maxwell, J. Maxwell. Okay, so there were kind of 4 laws to it. First law was Gauss's law of electricity, Gauss's law of magnetism. Actually, this has most of the scientists consider no name, but still some of them says that this is Gauss's law of magnetism. Okay, so this is the integral form. There is also differential form. Differential form is nothing but del dot d. So nabla dot d is equals to rho, where d is nothing but epsilon naught E. Okay, now Gauss's law of magnetism can also be written in differential form, which is nabla, and this is divergence of B, so which is 0. So no divergence of B is equals to 0 suggests that there is no diverging magnetic field. What is divergence means? Going out of a point. Okay, say something is here, and if it is going out, then it's divergence. And if it's going out and then again coming back, this is curling of a field. Okay, so if we see electric field when it was introduced, you see that there is a charge here and the fields are going outside if the charge is positive. Okay, so this is kind of diverging out. So there must exist divergence of a electric field. And when we started viewing the magnetic field, we always talked about curling of the field. Means there is a circular magnetic field here. Okay, so with this, you see there is no divergence. That means no magnetic monopole exists. This is how the interpretation of no magnetic monopole came into picture. Okay, after that, Faraday's law of induction came. Before that, Ampere's law, which was modified by Maxwell, James Clerk Maxwell, and the addition was this term. Okay, del D by del T. Okay, now here in Ampere's law, what it suggests is if we see its differential form, and it's very easy to interpret both of the forms, but it's way much easier to way much easier to explain the differential form or understand the differential form. So if we have curl of H, means a magnetic field strength is curling around a point, then that will be because of the current density flowing from the center. Okay, means if you say there is a curling of a magnetic field, that means from here there is a electric field, there is a current going in this direction. This was what was suggested by Ampere, by Ampere's law. But Maxwell saw that if you have a capacitor in between, okay, and you connect it to a kind of a AC source. Okay, so we all have learned in class 11 and 12 that capacitor passes AC, blocks DC. How is that? See, capacitor has empty space in between. So what is current? Current is movement of electron. Okay, movement of electron through a conducting wire. Now, what happens in DC current is you have one side positive charge and another side has negative charge. So what will happen? Negative charge will have most of the electron accumulation. So all the electrons will move from here to here. Okay. Now, if there is a capacitor over here, what will happen? This circuit will be broken, and the charge will accumulate. Negative charge will accumulate over here and positive will accumulate over here. So virtually you will see no current here. You will see only field lines from top to bottom, electric field lines. Okay, but when AC current is there, so what happens? One times electron goes like this, and for the other cycle electron goes like this. Means there is alternating cycle of electron flow. So it seems like current is passing through, means current is flowing through the circuit, but actually no electron is passing from this plate to this plate, from crossing the empty space or the media. What is happening? This is getting charged and discharged again and again. Okay, but what the conservation law and the this circuital law suggests that there must be something which is allowing the current to pass. So Maxwell suggested an addition over this term, which was del D by del T. And this was kind of groundbreaking, because this took the entire electrostatics and magnetostatic regime to the electrodynamic. Means in between this, the Faraday's law came, which says that the circulatory electric field produces time changing, time variant magnetic field. Okay, and this negative sign is due to Lorentz law, that it will be opposite in the kind of direction will be opposite. So this was already there, that curling of electric field will generate a magnetic field, but the concept means like the both things are linked with each other was not yet present. Okay, without something called a source term. So there was always a source term there. Source term is like a charge of accumulated electron is called a source term, source, and a following current through a wire is also a source to generate magnetic field. So when this term was introduced, this made the electromagnetic theory as a whole. Okay, this suggested that even if the field change is present, means the curling of magnetic field can also be generated by time varying electric field, as D is nothing but which is also called displacement current, and this is also called displacement current, del D by del T. D is nothing but epsilon naught E. So that is time varying electric field can generate curling of a magnetic field, or curling of a magnetic field can generate a time varying electric field. So this two equation, if there is no source term, so this term is essentially source term for electric fields. Okay, so it suggests there is a source, and Ampere's circuital law, when it was not whole, so J is here the source term. So this was also not present. So earlier it was only the curling of magnetic field was due to a source term. Now there is also time varying term. Now this two equation became the groundwork for the plane wave equation. So if there is no source term, the curling of magnetic field can be generated by time varying electric field, and the curling of electric field is generated by time varying magnetic field, and this two became the entire kind of base for the electromagnetics theory, means whatever the electromagnetics magnetism is right now. Okay, so this is how the story goes. Now this is something called mind map of the electric field theory. So don't bother about the numbering over here. So we have we took this from a paper which was about some kind of neural algorithm for studying electric field theory, but it's something goes like this. Okay, so the first came charge, something called charge was identified, then came something called interaction between the charges and identification of charge led to definition of charge, what is charge, and with this interaction definition of charges and interaction between them generated Coulomb's experiment, which led to Coulomb's law. And this is how everything is linked. You can go through this. When we will share this these slides with you, and this kind of creates how the theory is linked with one and another. And this way, this is the kind of a trick you should learn how to relate one particular concept with another. Okay, so moving on, then then in week 3 we went to something called antennas. So why antennas here? Now antenna is as defined as a transducer which can convert one form of energy to the other form. Okay, and this energy is electrical to radiation. So it can produce radiation energy given the electrical energy, and also do the vice versa. Given the radiation energy, it will convert it to your electrical energy, and which is also called signal. Now with the understanding of all the electromagnetism, we need to go for the practical field of this. So how we will detect those things? Because radiation, we can the visible light we can see, but the non-visible spectra, we know from the theory there is non-visible spectrum with there is a huge means there is an infinite bandwidth which we cannot see. So how we will detect those things? So there comes the concept of antennas and their relation. So the primary thing, if you revisit week 2, you will learn about something called Hertz dipole or infinitesimal dipole, where the theory is elaborated that if we have a very infinitesimal wire, and if we provide a signal, means kind of a signal to it, time varying signal to it, it will radiate isotropically. So infinitesimal dipole can radiate isotropically. Whereas if you want to go for practical designs, we will go to the lambda comparable antennas. So typically for wire antenna, lambda by 2 dipole is there, lambda by 4 dipole, lambda by 4 monopole is there. Okay, lambda by 4, that is monopole, and also lambda by 4 dipoles are also there. Okay, and these all depends upon few of the characteristics of the antenna as well as your system. So if you want to observe any electromagnetic spectra, let it be from the perspective of radio astronomy or communication, okay, you have to design in antenna as well as the system which will detect those signals. So for that, this there is something called max power transfer theorem that should be satisfied. So before proceeding to that, there are few things you should understand for the antenna. That antenna has, from the perspective of radio astronomer, you will always deal with something called full width half maxima, as we say it, and which is also the antenna people call it half power beam width. Okay, full width half maxima and half power beam width is one and the same thing. And there is also first null beam width. Okay, FNBW. Okay, sorry, FNBW. So these two terms radio astronomers use very frequently, and also with this also comes something called efficiency, aperture efficiency, which is eta, maximum time denoted as eta A, or ECD, something like this. And also there is something called beam efficiency. We'll means learn in few slides, means a bit later. Okay, beam efficiency. Okay, so these kind of terms are quite common. You will encounter in when you are doing any kind of data analysis and all in radio astronomy. Okay, so how this came into picture? So we have an antenna which will have its radiation pattern, a radiation power pattern, and with that you can find out the something called normalized power pattern. And when you equate this normalized power pattern, means this is normalized power pattern, when you equate this with 0.5 and 0, you get if you equate with 0.5, you will get full width half maxima, and if you equate with 0, you will get first null beam width. Okay, and also there's something called radiation resistance. This is very important if you are viewing in radio astronomy from instrumentation perspective, because you have to then design a system which will kind of log or record the data, electromagnetic data, for the further processing. So you have to design systems such that, or you have to design antenna such that it will follow the max power transfer theorem. Max power transfer theorem is it's a very simple theorem. Say if you have any voltage, means a source which is connected, means any source have its own internal resistance Rs. So any practical source will have its internal resistance, and if it is connected to a load, okay, RL, so maximum power can only be transferred if this RL matches Rs, and you can very well see, you can very well do the math by yourself. If that the power will be maximum at RL equal to Rs. Yes, okay. So for the simplest, so the power is calculated for electrical circuit. Power is calculated by V square by Rs plus RL. So this term will be maximum only when RL equal to Rs. Okay. Now, and this is also can be written as I square Rs plus RL. Okay. So, and sorry, this is here you will multiply voltage across this. We have to calculate voltage across this. Okay. So voltage across this will be RL multiplied by this Rs plus RL. So this is what the power equations looks like. Okay. Now this is only possible if this situation is matched. Now coming to the a formula which is very important, which is this effective area, which is equal to lambda square by 4 pi d. You can find the derivation and of detailed derivation of this in several reference books which we have shared in week 2 also. The names of the book we have shared in week 2. So the directivity is nothing but the area of maximal where the maximal radiation is occurring. Say if we have an antenna, like everybody knows how the parabolic antenna radiates. It radiates in a single direction like this. So it radiates in a single direction. So area, the way, if this area is minimal, the area of the area where it radiates is minimal, the directivity is maximum, but it is directed towards a single point. That what directivity means. If directivity is very high, that means antenna is pointing towards a very small point. Okay, and this term is linked with the gain of the antenna, which is equal to efficiency of the antenna multiplied by the directivity. This is how the gain is linked with the directivity. So you will have gain is equals to efficiency multiplied by your 4 pi area over lambda square. So this is your gain equation. And if you remove the efficiency, this will become your directivity equation. Okay. So moving forward in week, so we learned about, in week 2, we learned about the kind of a base for the entire radio astronomy, which is electromagnetism. Then in week 3, we learned about how to detect those electromagnetic wave. We need some kind of a sensor or a transducer. Okay. And we learned about something called antenna. As we move forward in the week uh, 4, we saw something called system. We introduced something called signals and systems. So whenever you receive something or some electrical wave or whatever data you are getting, we term it as signal. Anything which which contains information is signal. Whether it is processed or unprocessed, that doesn't matter, but it is termed as signal. So in this, what we learned, there is different types of signal. We can classify signals of different types. Also, we can classify systems also into different types. It's means there are means we will come to this later, what actually system means. So and something we learned also, like LTI, linear time invariant system. Okay, now, and in week 4 we also learned something called Fourier series and Fourier transform. The formulas for which are written over here. And with Fourier transform, there also came discrete Fourier transform and DTFT also. DTFT and then discrete Fourier transform. Discrete time Fourier transform and discrete Fourier transform. And also we learned something called FFT also. FFT is nothing but an algorithm to implement discrete Fourier transform. Now coming back to the point, what is system? System, we can consider it as a black box. We considered that as a black box in the week 4, which has its own response or the own characteristics, which adds on to the signal and we get some output signal. Okay, say for example, if you have kind of an amplifier, if you're putting if you're giving a sound signal to it, it will amplify it, and you will see the loudness of the voice increased. So there is a system, amplifier system, which did something to the signal and the output changed a bit. So the loudness changed a bit. So that is also something called proportional system, which it did nothing but added a gain to the signal. Added means multiplied a factor to it, and we get the output signal. So those are constant signal. So we introduce something called LTI, linear time invariant system, which means a system which follows linearity and also invariant with time. It doesn't change with time. And this is very important to us, because if the system is time variant, we won't be able to figure out what the signal was what is the signal at a particular amount at a particular time. Say if we have a time variant signal, time variant system, and if we give at t0 a signal and at t1 a signal, and if we don't know the how the variation is happening in the system, so how we will figure out at t0 t1, how we will back calculate the x of t, what has been input. Okay, so this is very important, because we are receiving signal from celestial sources, and using a system, we do some processing over it and save the data. But we need the information of the system to back calculate what x of t actually we are getting from the source. So the system should be very well defined here. Okay, so there are different means concept discussed in week 4. If you if you have any doubt, please revisit week 4's lecture and means get back to us in discussion forum. Now, in this only, we learned something about super heterodyne receivers. Okay, so super heterodyne receiver is something. Heterodyning is a word for something called mixing two things up. So here, super heterodyne receiver is a receiver which can down convert or up convert a frequency. Now, this is a very interesting concept, that to down convert or up convert a frequency. We know that from from class 11, 12, there are something called transformers which down convert and up convert AC voltages. Okay, but we can do similar thing with frequency. So this requires something called local oscillator, which is means which is providing a stable frequency, or the control frequency, we can say. Okay, so we have a local oscillator FL, and we get some signal from the antenna, and which is amplified and such that the signal doesn't go means doesn't attenuate to a level where we won't be able to detect it. Okay, now this is coming at something called some bandwidth delta F. Okay, now what will happen if we multiply these two? If you remember correctly, the trigonometric functions, as the Fourier series suggested, that any signal can be represented in the form of sine and cosine moves. Okay, now if you remember the uh, elementary trigonometry, so what will happen if you multiply two cosine terms or two sine terms? What will happen? You will get FL plus delta F and FL minus delta F, or this, or delta, you can write this like this also, minus F, sorry, plus F. Okay, now why I wrote like this and this? So these expressions are used when your received signal is at higher frequency than the local oscillator. Okay, okay, and this is used when you are kind of up converting your signal. Okay, so down conversion, so essentially it doesn't matter, because negative of any angle is reflected in that particular term, and it does nothing but just shift the phase a bit. Okay, so you can use any of this terminology. Okay, now after this we have a filter, and this decides what we are doing. We are up converting or down converting. Okay, we will be up converting if we are using a high pass filter and neglecting the lower frequency part. This is the lower frequency part here. This is the lower frequency part. If we are neglecting this, we are stopping it to propagate further into the system, so we are up converting. And if we use a low pass filter and we remove the higher frequency to propagate in further in the system, we are down converting. So these are the concept, but what we use in radio astronomy is mostly a down converter, or we use two-stage heterodynamic receiver, where we first up convert, then filter, then down convert. And this two-stage is because in higher frequency, filter designing is easier, and filters means and the frequency selection is easier. Okay, so this was a bit kind of a extra tidbit for you. Now we also saw that how the entire chain will look like. Means like a generic chain for the our radio observatory will look like. We will have an antenna, and there will be something called RF front end, which will consist of two LNAs, low noise amplifiers, and with combination 2 or 1 based on the signal strength, and a pre-filtering. Okay, pre-filtering, which can be low pass, high pass, band pass, based on the band you are observing. Okay, now then it will come to the back end using RF cables. RF cables, or nowadays it's something RF over optics. There is something you can read about it. So RF backend, and RF backend generally will consist of heterodyne receiver if you are observing at high frequencies. If you are observing within hundreds of megahertz, hertz, you can means there are systems which can directly convert those into digital data points. So there is no heterodyne receiver for that. Heterodyne receiver used. Okay. Now this will be consist of means LNA combinations of filters, then again high gain for high gain, RF amplifier, and heterodyning, whatever the heterodyning principle suggests, LPF, then again amplification if needed, and there will be a digital backend also. So the backend consists of RF and digital. So what it does, it will have ADC in it, which will convert analog means the continuous signal into discrete form and store it into some memory. And also you can that can be processed further with Fourier transforms and all different things you can do with the saved data. Now what is LNA? And from this we came to something called noise figure, noise temperature. So we studied something called noise power. Noise power is something KTB, where K is Boltzmann constant, and temperature and bandwidth. So for a resistor to be at a temperature T, it will generate P amount of noise power. So this noise power concept is very important to us, because whatever we are watching is due to some kind of radiation mechanism. Okay, so in week 5, I believe, week 4 or week 5, okay, so in the first 2 weeks, we also studied about something called radiation mechanism. So there are popular radiation mechanism. One of them is black body radiation, where the Planck's law and Rayleigh-Jean's law, Stephen Boltzmann law, all these things comes. And there is something called non-thermal radiation, which you studied in, I think, week 8 or 9, which consists of synchrotron radiation or cyclotron radiation. Okay, where a charge part, and Bremsstrahlung law radiation, where a charge interacts with the fields. Okay, or the media, because of which the radiation is generated. Okay, now coming back to the topic. So this is very important, because what we are observing is the sky, whatever noise coming from the sky, and from that we will see further how we can relate it with our we can relate it with our source temperature and all. Now noise temperature is given by Tref, noise figure in dB, and -1. So noise figure is a kind of a figure of merit for a RF system. And noise figure is defined by SNR at input to the SNR at output. Okay, signal to noise ratio at the input to a signal to noise ratio at the output. So the maximum value of a noise figure can be 1, because if system, whatever the system you have, contribute nothing to the noise, doesn't contribute anything, any noise to the system, so you will get whatever the SNR at the input was, signal to noise ratio at the input was. Okay, so the maximum you can attain is 1, and in dB, if you say, it will be 0 dB. Okay, in dB scale. Okay, it will be 0 dB. Okay, now if you see here, everything we are connecting to each another, one to another, one to another. So for this kind of connected systems, how the noise figure is calculated? Noise figure, that is also called as cascaded noise figure. Now, the cascaded noise figure is given by this equation, which is also called Ferris equation. And now this suggests that F means this came from something called control system, where you look from this side how the noise figure will be. So from this equation, you can see that the first amplifier in the system sets the noise figure for the entire system if it has a very high gain. If it has a very high gain, then this term will be almost negligible. This will be also almost negligible, and so on. Now, here, if you see the first, we will put LNA to set the noise figure. And again, after a long wire, we put an LNA such that we don't contribute much to the noise. Means we don't contribute noise to the signal. Okay. Now, with this, all the concept of noise figure and all, and also the radiation mechanism and everything, we went to single dash radio telescope observations. Okay, so wherein we studied how a single dish can be used for observing any celestial objects. So with the general formula of the power at the whatever you have collected in this recorded, we said that the flux from the source multiplied with the collecting area into the bandwidth is whatever the power we will receive from the telescope. Means flux you can consider as a kind of a flow of water or something, and you are collecting it in a big dish, which is telescope, and for a particular amount of bandwidth. So that much amount of power you will receive. And from this concept, we went to elaborate several features of the single dish telescope. Now revisiting something called what are the basic measurements which is done using single dish telescope. So in a electrical system of a single dish telescope, we will we will get something called voltages. So any electrical signal you will get as in voltage. Now using those voltage, how we will say that what we are observing. Okay, now if say we have a system of single dish telescope, where we will have a telescope, and with which we have some system attached, and it is recording something. Okay, it is recording something. Now if we switch on the antenna, what we will get? We will get antenna temperature plus system temperature, whatever the noise temperature contributed by the system is. Okay, and if we cut off the antenna, whatever we are getting, whatever we will get will be due to the system temperature. So in general, what we will have, if we subtract these two, we will get something proportional to the antenna temperature. Means we can figure out what the antenna temperature is provided that we know the gain of the receiver and Boltzmann's constant with your voltage, and alpha is a proportionality factor, which is also known as responsivity of detector, which is in volts per watt. Okay. Now with this knowledge, what we can do, we can determine the system temperature, or we can point to something called calibrated temperature. Means we have a fixed temperature source or something radiating at a particular noise temperature, and from that, what we can calculate, back calculate the system temperature. So if we point our antenna towards the calibrated source, okay, so we know the temperature of the calibrated source. So uh, so the vcal will be, looking at the previous equation, it will be some alpha g Boltzmann's constant delta nu into t and plus t sys, and this t and is nothing but t cal, because we know the source what we are watching and what its temperature is. Okay, so if we divide it by off, v off, means if we switch off the antenna, which then we will have this term, correct? We will have this term, and if we do that, we will get the ratios of the temperature. And if we do the mathematics, some mathematics, we can find out what is the system temperature here. Okay, this is generally how a radio astronomy facility calculates the system temperature. Okay, now also, if you take it to a step further, then we can calculate antenna temperature. If we know the system temperature from the calibration, we can calculate the antenna temperature by the same mathematical calculations. And with that, we can move to something called what are the uncertainty we will get in the antenna measurements. So those amount of uncertainty means what you expect and what you got, which is also represented in RMS, root mean square error. Okay, what mean to it? So if you see this, there is lot of points which are not on the line. So mean is going somewhere from here. Okay, this is the mean line. Okay, but you have the outliers. Now this is what error is. So with that, we can calculate RMS, and also we can see that the standard deviation or the mean fluctuation, whatever the this is capital RMS. So the fluctuation can be determined as the T sys over the del T and del nu, where del T is the integration time and del nu is the bandwidth. Okay, and this is the integration time, means the time for which we observe the source. Okay. Okay, so if you see that if we observe a source for a longer duration, or over a large bandwidth, the fluctuation will diminish. Okay. Okay, so and as I said earlier, we also have few concepts like aperture and beam efficiency we will encounter. So with this here, all the measurements for a single dish, means with our elementary knowledge, what we can solve are till here, and then comes something called aperture and main beam efficiency. So aperture efficiency is nothing but, say, anything you design, there will be some kind of faults in it, or it won't perform as ideally it should. So you will have something called geometric area, which will be the true area, and also you will have something called effective area, which is less than or equal to the geometric area. So with this, efficiency comes into picture. Comes into picture, and efficiency of an uh, area of a telescope is defined as an effective over the A geometry, okay, or the original area. So this is always less than 1, less than equal to 1. Now as we know that the dimension of the antenna governs the whatever the your full width means full width half maximized or the half power beamwidth is, and you can calculate the solid beam angle using that. Now you know that the theta is equals to your lambda by d and some proportionality factor here k, okay, k lambda by d. Now using this and the approximation of our solid beam, what we can calculate? We can calculate the main or the solid beam, effective solid beam, okay, effective solid beam considering the effective area, and we can also calculate the kind of a 100% efficiency solid beam, and we can calculate beam efficiency eta beam as effective over 100% efficiency. So and this you will get always greater than equal to 1. Why? Because if area is maximum, the diameter is more, and the whatever the theta value or the resolution you will get is smaller. So the degradation in your collecting area will result into broader beam size, okay, and that what the beam efficiency means here, okay. So with this we extended our knowledge to the something called beam dilution, or whatever the temperature we are observing from source, to calculate the brightness temperature of the source. So we have the we know what is the solid beam of the antenna, and if we provided the solid beam of the source, we can calculate how much of what will be the brightness temperature of the source if we also have the antenna temperature. Now this equation is valid to calculate the source temperature if and only if these are provided and one of the term is provided. Now considering the setup, what we will have, we have a clear sky and we have a source here, okay. Now if we have an antenna which is observing like this, so it will cover some part of sky also. Say this is at a temperature T1, and this sky will also have its temperature T2. Now the antenna temperature TA will be T1 plus T2. Now how much portion of it will be T1 and how much it will be T2, how much the contribution of T1 is, can be calculated using this equation with a slight modification, where this will become delta TA omega source by omega antenna into brightness temperature. So if the source size is smaller than your antenna size, then your incremental antenna temperature due to the source can be related by this, okay. And this term is also called beam filling factor. So this is what I explained earlier, that what is aperture efficiency and what is beam efficiency. Okay, now let's skip this. Yeah, so here, so with any telescope facility, there is a term we call that sensitivity. Means how sensitive is the your observational facility. Okay, now that, if you remember clearly, we said there is a fluctuation term. Okay, antenna temperature fluctuation term, which is proportional to system temperature over the observational time and the bandwidth nu. Okay, so this is how we suggested it was related. Now if we are talking about uncertainty or the sensitivity of the telescope, that means this will play a role. That means fluctuation of the antenna temperature will play a role in this. So which can be represented by this equation. Why this equation? Because we know that the power received by a telescope is nothing but f nu into Boltzmann's constant delta nu and temperature. Okay, uh, it is sorry, effective area, not temperature, effective area. Okay, so it is we knew that this is related like this. Now from our general knowledge, we can say that f nu will be related to the power received by just by crossing over all the terms, a effective delta nu. So, and with all this manipulation, we arrive at this term where the sensitivity of any observational, single dish observation facility is inversely proportional to the effective area and the integration time and bandwidth. Now, this makes sense. How? If you have a very large collecting area, definitely you should say that, yeah, we have a very large bucket to fill the radiation with. So we should have more sensitive observations. Okay, so this is inversely proportional, which suggests that. And if we observe a thing for a large amount of time, so that we will add, means kind of add one reading to another, and that will become kind of redundant reading. So if we have large amount of observational time, that will also increase our sensitivity. So this thing holds logically also. So if you want to view derivation, we there is something called Blue Book, which is you can find on GMRT, where a detailed derivation of this is given. Okay, you can refer to that, and if you don't, if you are having trouble in understanding, please get in touch with us. Okay, so and similarly with that, we can relate the whatever the minimum sensitivity with the SNR also, signal to noise ratio. Now, how is that? So the signal to noise ratio is inherent in the system. Now, whatever the SNR we were getting, okay, from the sky, will be multiplied with the whatever the fluctuations, the minimum sensitivity term. So this is nothing but like this. So minimum detectable signal or the flux density, you can based on SNR. So your SNR is nothing but whatever the minimum flux you can detect, this minimum flux what you can detect governed by SNR. So minimum flux over your sensitivity, sensitivity of your system. Now, how this is always done kind of practically. You point means what we do here, we try to find out some instructable backyard interferometers, as well as a single dish observation we do. So we have horn antennas and horn antennas which we point towards the center of the galaxy and take a reading in a means periodically. So what we do, we point towards a fainter and fainter sources, and we see when we are not able to detect anything. So this is a kind of practical thing or a makeshift way to see what are the minimum flux you can detect. And we know already the system temperature and the time, okay, the integration time and all this stuff, and we can relate it to, with this we can relate it to what is the minimum, what is the SNR of the entire system. Okay, so but suppose we have a telescope with gain G, and this is all talking in practical sense. If we have a telescope with gain G, okay, then we can approximately relate it with the flux density which we are observing, multiplied by the gain antenna and the time of observation multiplied by the bandwidth over the system temperature. Now this will give you the rough estimate of the SNR, or what you will require from your system. Okay, means rough estimate of the SNR, signal to noise ratio, and provided whatever the noise figure of your system is, you can quote whether you will be able to detect or not. Okay, so with this I will stop here and take few questions if there is any. Okay.
Sir, in the here the last one for approximate SNR, here you have written FNU. Here FNU means the minimum detectable flux density, or is it the flux density from observed from the source? The last one.
Okay, so this, see, SNR doesn't mean you are calculating only for the minimum. Okay, so to clarify this point, in say SNR, any signal will have an SNR. Let it you are say you are providing a 1 volt signal and a 0.5 volt signal. Both will have an SNR. Maybe 1 volt signal will have a very high signal to noise ratio, and whereas 0.5 volt will have very low. Okay, if you want to find what is the minimum flux you want to detect, you should know the signal to noise ratio to know what is the minimum flux you can detect by using your system. Okay, means how much SNR you will need from the signal so that your system can detect it. So if say going back to the concept of noise figure, which is SNR at input to the SNR at output. Okay, now say you have a very high noise figure, means like so so this is nothing but SNR at output will be is equal to SNR at input by NF. So if you have a very high noise figure, means system is very noisy, you will have a very low SNR or very less chance of detecting the signal. Okay, so for SNR for any source you are observing, so this FNU can be anything what you are observing, not only the minimum one. If the SNR value is very high, that means you will easily detect that source. If SNR is very low, that means you need to increase either observational time or lower your system temperature or increase the bandwidth of operation to increase your detectability of that source. Am I clear?
Okay, sir. So you are saying that this FU can be both the value that we observe as well as minimum, which depends on the SNRs which we receive at the input.
Correct.
Okay.
Any
Sir, in exams, what will we be asked based on this?
uh, so in exam, it's I think from our perspective, it's very easy and straightforward questions only. There is no kind of a mix, means like going around the point. Everything is straightforward only. So that much I can say, that it is everything straightforward. If you know all the concepts, you will easily able to do it.
Okay, sir. No, I'm asking with this particular SNR thing, whether we will be given the minimum detectable flux density C or the observed flux density. Like,
Given everything there, means like the point of this revision sessions are that only. Whatever the important means concepts are there should be revisited once again. Okay.
okay, sir. Okay, sir.
Okay. Okay. So anything else from someone? Any other doubt till now? No doubts regarding assignment doubts? Anything?
Sir, in week 11 assignment, there are a few doubts.
Sure, go ahead.
Sir, in week 11 assignment, question number. What?
Wait.
Question 1. Here we are asked to find the speed of the electromagnetic wave in the medium with dielectric constant 3 in kilometer per second. So are we supposed to write only the decimal parts without the 10 power 5 term, or the decimal part with the 10 power 5 term?
Okay. Let me. Pardon. Come again. What you are trying to say?
In the first question, we are asked to find the speed of the electromagnetic wave passing through the dielectric medium in kilometer per second. So after finding the speed, I'm supposed to write just the decimal parts or the decimal part along with E plus 5.
Everything. So we didn't wrote any orders, right? So you have to write the means the entire stuff. Say it came out to be 1 lakh, for example. You have to write 1,0,0,0,0,0,0 something like that.
So can we write like 1 E plus 5?
No Mentesa format.
Okay, so the whole thing.
No, whole
thing. 1 followed by 5 zeros, something like that.
Correct.
Okay.
So this thing also is there. So means in exam also we have specifically mentioned that in what order you should write. If the order is not given, you have to write it means like the entire thing only. Okay.
Okay. Also here for this week's assignment, we are given for formulas and hints. Will the same things be given in the exam too?
Pardon. Come again.
In this week's assignment, we are given formulae and hints for some specific questions. Will the similar thing be done in the exams too?
I think for some questions, yes, but sir knows. I don't know the thing because sir said the paper. So means I think for means where the formulas have lots of constants and all, those things will be given.
Yes, sir. And also for the 10th question, we need to find the RMS value and multiply it by 5. So they are basically asking us to find the 5 sigma value, sir.
Question number
10.
10th. Come again. What was your question?
Are they asking us to find the 5 sigma value?
Not 5 sigma, only the sigma value.
So using 5 times the RMS noise as a conservative upper limit.
Okay. No. There, I think the thing they asked 5 times the RMS. Yeah, but they asked the minimum amount of the time. So here they asked quantity is time.
Yeah, so we are given sensitivity, so multiply by 5 and use it like that I'm asking.
Yeah. You have to do that only.
because 0. We are given sensitivity limit of 0.3 Jansky. So are we supposed to multiply it with 5? Or is
No, no,
this
no, no, no.
is
No,
this
minimum,
0.3?
minimum will be always you should means equate with the same value.
No, what
So
I'm asking is
here
this
they are
0.
saying
Okay.
here it is said the minimum of 5 SNR detection. Okay, so if you multiply the sigma value by 5, that means the sensitivity you are means like decreasing by 5. Means if you means what is the sigma value? Sigma value gives you the deviation, kind of, right?
Yes,
If you
sir.
multiply it by 5, that means you are deviating more.
Okay.
Okay.
So, no, what I'm confused about this is we are given a sensitivity limit of 0.3. So, are we supposed to multiply it with 5,
No,
or is this
you don't have to.
0.3 itself is the 5 sigma value?
Yeah, 0.3 is the 5 sigma value. You
Okay.
can go with that.
Okay, sir.
Wait. By the way, one thing you might have missed, that sensitivity 0.03 sigma, that is in Jansky, but you have to calculate the delta F nu, sigma F nu. You need to calculate that. It means like variable inserting the delta T. Okay.
No, I don't get it. What you said?
Wait. So hold on a second. Wait. So pardon me, you were right. Okay. So I kind of jumbled up. So here it said that 5 times the RMS noise you have to calculate, right? So this means that whatever the deviation you are calculating, okay, that should be means you don't have to multiply it by 5, but you have to divide it by kind of double the value, means by 10. Okay. So this is because you have a kind of SNR generally. Okay. So okay. So the 5 times the SNR RMS noise, it is mentioned the RMS noise. Okay. Now to detect this using a beam, okay, half of the beam, this should be should be able to detect from half of the beam. So if you are using a full beam, that should be like 10 times the SNR. Okay. Now these all things means I didn't cover this after the half of this. I would have covered that part, that whenever we calculate the sigma values, okay, and when we relate with the SNR, it is done for the half of the beam. Means a beam pattern is kind of when we compute with the power, the normalized power, we multiply it by the angle we get, we multiply it by 2, right? Correct?
Sir. Yes, sir.
Okay. So now when we are dealing with power, and that means we are dealing with the half of the beam. So if we consider full beam into picture, the SNR comes around to be 10.
Okay. 10 times. No.
So, so the minimum signal will be whatever the limit given is 0.3, you should divide it by 10. Okay.
Divided by 10.
Yeah, divided by 10, because you will be using the entire beam to detect those things. And then using that, you can calculate whatever is the minimum time that you should observe. The minimum time will only come if you are utilizing the entire antenna setup, right? That's how it is.
Oh, and here 5 times the RMS means yes, the SNR is 5. Is that what they are saying? The SNR here.
No. SNR. Yeah. RMS noise. This is SNR only. Yeah. Correct. SNR
So
only.
SNR is 5 in this question.
It's not exactly SNR. This is RMS noise is 5.
Okay, so let me summarize what you said. Tell me whether I'm correct. Here we are given the sensitivity limit of 0.3 Jansky. So, and we are asked to find, you take 5 times the RMS noise as the conservative upper limit for null detection. And you said earlier we did it for half the beam. So since we are using multiple antennas, we should do it for the full beam, which means twice this thing. So the sensitivity limit is 0.3, and 10 times this means 0.3 into 10 or divide by 10.
Divided by 10.
Okay. And here the correlated efficiency and the antenna efficiency are supposed to be taken as one, sir.
Yeah.
Okay. And using the other variables, we need to calculate for delta T.
Correct.
Okay, sir.
So the RMS noise means the deviation in noise, not means it is not exactly the you can say SNR, signal to noise ratio.
But the sense in the previous survey, the sensitivity limit was 0.3 Jansky, which did not detect this source. So that was the phi sigma value for the previous survey, or just the sigma value for the previous survey?
It was wait, let me using 5 generally what we do is, if we want to do any survey, we go either 3 or 5 sigma value kind of below the sensitivity level. Means the sensitivity level should be 3 or 5 sigma kind of below. Okay. So generally, this is the kind of a thumb rule. Means if you want to do some sensitive observation, you should be well above the sensitivity level.
Yeah, well, I'm confused about that part, sir. I've already used TGS survey, which has 1 sigma value of 5 millijansky. So whenever I plot contours, I usually take this for 15 millijansky as 3 sigma value and plot contours. So yeah, with that being in mind, here we are given the sensitivity limit is 0.3 Jansky. So what do we multiple? Aren't we supposed to multiply this with 10? Like you said, why are we supposed to divide?
Say you weren't able to detect using that 0.3, okay, sensitivity. Now you want to detect that using 5 times the RMS noise as a conservative upper limit.
Okay.
Okay, means that this 0.3 Jansky should come when you're observing observing it when means kind of like 5 into your 5, not 5, 5 or 10 times into your sigma new value should give your this sensitivity limit.
Oh, okay.
This is meant this is like that. So you have that kind of conservative upper limit to it, and then do this.
Okay, so now I understand.
Okay. So
okay,
the trick here is that conservative upper limit means like you're defining an upper limit that sigma deviation should be like this. So it should be lower than the previous sensitivity level.
Okay, sir.
Any other question?
I think that's it for now.
Okay. Anyone else?
And you haven't taught us about this plasma frequency part. in question 6.
Yeah, sir will cover it. Means soon you will get the video about it. So for the assignment purpose, I think the plasma frequency formula is already given.
Yeah, it's given. No, I'm asking the concept is not clear, covered.
Okay, concept. So I can I won't be able to go through derivation, but I can tell you how that is there. Is that okay with you?
Okay, sir.
Means how that concept came into picture.
Okay, sir.
Okay. Now, let me. Is there any something whiteboards here? So. So you are able to see the whiteboard, right?
Yes, sir.
Okay. Cool. Now, generally, what happens? Plasma is plasma consisting of charged particle. Okay. Generally, free electrons and means your not protons, but the ions, which will I say that I plus. Okay, free electrons and ions. Now, this means this happens in the means Earth's ionosphere also in solar wind. Okay, now solar wind, interstellar plasma, all these things. So those are what essentially a hot gas. Okay, very hot gas, and that will have two kind of radiations. Okay, one which is due to temperature and will be black body in nature. Okay, this will be there due to the temperature of the plasma, and the other radiation will be due to the vibration of the molecules. Now, say any plasma will have n number of electrons in it. It will be moving and colliding with each other. Okay, which carrying electronic charge, and the square, we are doing the square because the electrostatic force is related by the QQ square, means charge of two particles. Okay, and this will also depend on the mass of the electron, and there is one more quantity, which is the permittivity of the media. Okay, so this is what the plasma frequency is. Means this is the equation, but the vibration what contributes to the your radiation. So if electron is moving in a means in a cloud, okay, if electron is moving in a cloud, what will happen? It will interact with other means ions or electrons. Okay, that will means accelerate or decelerate the motion of the charged particle. Okay, now this WC is the cutoff frequency. Okay, cutoff frequency means the highest frequency which can be attained in that plasma. Okay, so higher the number of the charged particle, your cutoff frequency will be that much high. Okay, now if you have more and more charged particle in a region, okay, so that will contribute to more higher frequencies, because your collision can means two particles can collide with one, the acceleration can be more, or due to that. Okay, so this is how plasma frequency happens. Means those are all interaction of means particles which contributes to the radiation. This is kind of a phenomena. Means this is also, I think you will find this in there is a part in physics, right, where we something Maxwell's I don't remember the name, but the some there is random processes, right? Uh, Maxwell's distribution, yeah, Maxwell's distribution and Boltzmann distribution, all those things. You will find a bit of theory there. Means if means the from thermodynamics, right? From thermodynamics, yeah, from thermodynamics concept, you will find how this particle oscillates in a means when it is means confined into a area, or there is n number of particle in a space. So a part of theory comes from there, combined with your electrostatics. You will get means all these equations are there. So I don't actually remember. There is a graduate level physics book where you can find a detailed derivation of this. uh, I think it's by some author, author Ghosh. There's a author Ghosh by that person. There's means it has very beautiful derivation there. I will share it with you in drop me a message on discussion forum. I will share that book's name with you to you can go through it. Okay.
Okay, so but is this the frequency of the photons that can be maximum frequency of the photons that can be allowed to pass through the plasma medium, or the maximum frequency with which the particles are moving or colliding with each other?
Actually, I will say both.
Both.
Yeah. So what happens, why we are saying that the ionosphere blocks that? Because ionosphere radiates in those amount of frequencies so much that we are not able to figure out what is the signal sent by us, or it is there. And if the frequency matches the oscillation, it will be absorbed in the system. Okay.
Yeah, like resonating.
Yeah, resonantly. Yeah, it will resonate. So that's why it blocks. So maximum resonant frequency is omega c. So the frequency which is emitted by the ionosphere, as well as which can be resonated and means absorbed by the ionosphere, is omega c. And above that, it won't be able to resonate. And so just like your what happens with microwave. Okay, why the water boils in microwave. So same concept. The resonance frequency concept is here. And
Okay,
if you see the spectra of the water line using spectroscopy, you will find the same frequency what your microwave oven is emitting.
Yeah,
Okay.
because it absorbs that frequency and it rotates. And the
Correct.
rotational angular frequency of rotation is same as the angular frequency of the microwave photons.
Correct.
So same effect also happens here. Okay.
Yeah. And this omega c changes, interestingly, it changes from day to night. If we are observing from Earth, this omega c changes is different in day, different in afternoon, different in night. Because the ionosphere, the range of the ionosphere, the width of the ionosphere changes the entire day. And there is a kind of a wide range of studies which is going on to figure out how we can model the ionosphere such that we can negate all those effects due to the ionosphere. So ionospheric study is also, you can say, is not only a part of engineering students, electrical engineers and communication students, it is also a part of astronomers also. So we also need how the ionosphere behaves. Okay.
Sir, does this hold only in the case of ionosphere, or can we also apply this plasma frequency concept to intercluster medium too?
Yeah. Same. You can do there also, because this is not dependent upon anything called sun or atmosphere. It is only dependent upon the number of electrons you have there. Number of means what are the mass of electron. If it is relativistically moving particle, so the mass, it will go into relativity, general relativity, and it will become, whole thing will become very complex. So being in means if it was a stationary interstellar plasma, same will apply. Same thing will apply.
Okay, so if we have observed diffuse radio emissions from galaxy clusters of, will it be due to this, or will it be at this frequency?
Pardon? Come again.
If we observe diffuse radio emissions from galaxy clusters intercluster medium, will it be at this cutoff frequency?
Diffused emission
Of the intercluster mix in the case of galaxy clusters, will the plasma radiate at this frequency?
Actually, I don't work on diffuse emissions, but whatever I have seen and read paper about, it's in a few megahertz range, and I don't think so. That is related to this omega c, and those diffuse emission is due to the I think the diffraction of the due to the diffraction of the media, diffraction and scattering of the media. Whatever the cluster, the media of the cluster is, means those contribute for diffusion more than these things. Means this cutoff frequency.
Okay, sir.
Okay.
Also, can we use this formula to infer the electron density of radio galaxy jets?
Yes and no. If the jet is in non-relativistic speeds, then yes, you can use these concepts. But if it's a relativistic jet, then you can't.
So, but jets are inherently relativistic.
Yeah. I know that, but I said yes, because if you go very far away, means that the end of the jets, where the means like if you see a jet, it will be like going, it will be here and there. Here you will find a diffuse cloud like this. Okay, something like this you will find.
Yes, sir, the lobes.
So yeah, the lobes, correct. So the lobes is in kind of non-relativistic speeds. There you can apply these things if you want to study the lobes.
Okay, sir.
Okay. Anything else?
Excuse me, sir.
Yeah, sure.
Sir, in this case, what does jet mean, sir? Is it a quasar, sir?
Jet is generally what you means. Okay. Jet is a word for a beamed emission.
Okay,
if
sir.
I say beamed emission of a particle, that is what jet is called. So it can be quasar, it can be your black hole also.
Okay, sir. Yeah, sir.
Even pulsar doesn't come under jet categories, but it gives a beamed emission of electromagnetic wave. If beamed emission of charged particle is there, we call it as jet. Because when charged particle comes, you can apply the concepts of means laminar flows and all those things, where the means movement is due to the your means what say longitudinal motions. Okay, movement is kind of longitudinal, you can say. Means just like sound wave travels, that the behind the faster moving particle hits the slower moving particle and the energy is transferred like that. Those kind of thing comes, so then we term it as jet. Am I means making sense or clear?
Yeah, sir, I understood, sir.
Okay.
And sir, in week 11, question 1, sir, the unit hasn't been printed clearly. What is it supposed to be, sir?
It will be in kilometer per second only. Means you have to write the entire thing.
Okay,
so it's
sir.
one followed by 5 zeros.
Okay, sir.
Okay.
And sir, I had a few other doubts, sir. In last week's session, I asked you about some book recommendations, sir. You said us to refer Fundamentals of Radio Astronomy, sir. So there are 2 editions of that book, sir. One is
both. So the first, if you see the first, I think 5 weeks, 5 to 7 week covers the first book, and the next is covered in the second book.
Okay, sir. And sir, is there any possibility to get a PDF or something of that book, sir? Because it costs around 4,000 rupee each, sir.
I don't know, but there are many other methods. But you can contact your library to have those things. Otherwise, you can follow. There is means you can find white book as well as blue book. White book is by I think VLA, and blue book is by GMRT, which will cover the instrumentation entire from instrumentation, and as well as some science part as well. And there is something called a book which is there's an image synthesis book which you can also read, which covers all the means data processing and all those part.
Okay, sir.
Books. Yeah. So I will share the kind of names of the book which are freely available in the website. Let's say internet. Okay.
Okay, sir.
We will share.
Sir, I got a PDF of a book called Radio Astronomy by John D. Krause. Is that going to be good?
Krause, right?
Yeah, sir.
Yeah. So that will be good. Actually, the Krause's books are generally very simple to understand and all those things. So that actually that will be very helpful, because it means I have read that, gone through that it's written in very easy sense, and but the portraying of that thing is from a kind of a instrumentation perspective.
Okay, sir.
Okay. So for the science part, you need to go to some image synthesis, interferometer and image synthesis book. One is there, which is freely available online. So I will share the name of the books which are readily available online. Okay.
Yes,
so
sir.
You should know Blue Book and White Book. These two books are there by GMRT as well as VLA. These two books are referred by everyone. It's like when they are trying to understand anything. Okay.
Yes, sir. Yes, sir. Sir, in week 10 assignment question 7, sir, since it was not printed completely, you said that it will be given 0 points, sir. So is it still the case?
Yeah, it's still the case.
So we can skip that question, sir?
Yeah, sure. You can skip. Yeah, or you can put
sir.
any value, whatever you feel like.
Yeah, sir. And sir, in week 9, we had discussed a few discrepancies in the last class, sir. So by when can we expect them to be updated, sir?
We have already related that discrepancy in which one?
Sir, question 13, sir, the range was too small to fit all
that has been relayed, and that will be updated soon. I think
sir.
Announcement is already done for that, or no?
And I don't think so, sir.
Okay, I will look into it.
Okay, sir.
Okay.
Yes, sir. And sir, when can we expect the hall ticket to arrive?
Hall ticket maybe next week. Maybe.
Okay, sir.
I will get in touch with the NPTEL and let you know.
Yes, sir.
You can drop a mail in discussion forum. Surely the admin staff will also reply to that.
Okay, sir.
Okay.
Yes, sir.
So, sir, can you also share the list of concepts that are only there for completeness for all the 12 weeks?
I am kind of sharing what you need right now, right? The first half lecture, the revision.
Everything. Yeah, that's what is essential. But sometimes I'm confused whether this is essential or not. So, can you specify which are not, which are only there for completeness sake?
If you want to know from exam purpose, follow the assignments. Okay.
Yeah. Okay.
That will be more than enough to get good marks. Okay.
Okay, sir.
Okay.
Okay, so what is the minimum cutoff?
Pardon?
What is the minimum cutoff, sir,
For what?
for this exam?
I think 100 mark paper is there, 30 marks is cut off
Okay,
for
sir.
passing. Okay, and I think these things are written on the this also, some instruction pages or something like that also of the course, I believe.
Okay, sir, I'll check that.
Sir, if we go through the assignments and the solutions and examples properly, sir, do you think it's possible to get 65% in the exam?
Easily.
Okay, sir.
Okay, so any other doubts, whatever I have revised till now?
Sir, not exactly a doubt, sir, but sir, why didn't we get a example video for this week, sir?
It will be uploaded by tomorrow. Everything will be uploaded by tomorrow. Whatever the additional video, example videos we are trying to say. So there
Sir,
is
but today is the last day for week 10, no, sir.
week.
10, sir. Week 10.
So do you have any problem in assignment? Means you can discuss, right?
Yeah, sir.
So if you have any, I can relay it to you. Means like I am here for that only.
Okay, sir.
So if you have any doubt, means besides those means whatever I said, I gave the formula also for one of the questions which was not covered, right?
Yeah, sir.
So good. Means as all the assignments that are very straightforward and easy. Means sometimes we also do some mistakes in calculations, and you rightly means point out, which
Yeah,
is very
sir.
good. Be active like that. Okay, so
Yeah, sir.
most of the things are from the most of the things are revision, and few of the things which are new, but that will be covered. Okay, so don't take
Yeah, sir.
tension. Means enjoy the learning process.
Okay, sir.
Okay,
And sir, just one doubt, sir, that if we have to find the total gain of an amplifier sequencer, do we just need to multiply the gains?
pardon, come again.
Sir, to find the total gain of an amplifier sequencer, do we just need to multiply the gains, individual gains?
That depends. If you are if you are in dB scale, you have to add. If you are not in dB scale, you have to multiply.
Okay, sir. So in dB scale, we have to add them.
Yeah.
And sir, last week you gave us few formulas, sir. So you gave that noise figure is equal to noise figure of first receiver, then plus noise figure of second receiver minus 1 by G1 and so on, sir. So that minus 1 is only for noise figure, right, sir?
Yeah. For
Not for
noise
the temperature.
No, for temperature it's will be T only.
Okay, sir.
So you are asking about question 10, means assignment 10, question 4,
4
right?
and 5, sir. 4 and 5, sir.
4 and 5, correct, right, correct. So their gain is in linear scale, not in dB scale. Okay, keep that in
Okay,
mind.
sir. So we have to convert it.
Yeah. So if
Okay,
you
sir.
want to write in dB, so you have to convert it.
Okay, sir.
So for effective temperature, the formula is T effective is equals to T1 plus T2 by G1 plus T3 by G1 G2 plus so on, like that sequence goes on. Okay.
Yeah, sir. So, sir, in Freeze formula, we can directly use in linear terms, or do we need to convert to decibels?
No. Freeze formula is only for linear term.
Okay, sir.
Okay. Then
Yeah, sir.
after that, you have to convert into dB.
Okay, sir.
And
sir,
this temperature is in Kelvin only. So
yeah, sir.
No conversion. Yeah.
And sir, you also mentioned about the receiver temperature question, sir. That was in week 9, sir. So you said we have to take the linear value directly for noise figure. So for what range do we take it directly like that, sir?
See, if it's around 3 dB or less than that, 3 or 4 dB less than 3.5, less than 3.5, you can take it directly.
Okay, sir. And otherwise, we need to do that logarithm, right, sir?
Yeah, yeah.
Okay, sir.
Sir, in the last 10th question, since the beam is given to be a symmetric beam, so find the beam solid angle, we need to directly square the angle in the half power beam. Is it correct, sir?
Yeah, that is also correct. And the more correct approximation is pi by 4 ln2 multiplied by the square of the angle. Okay, half power angle.
Okay, so
Okay.
we
So, but the range is big. Where if you directly square it, also it will come.
pi by 4 ln 2 square of the half power beam width.
ln natural log.
Okay, that gives the half power solid angle.
Correct.
Okay, sir. So both the direct square answer as well as that square multiplied by pi by 4 ln 2 are correct. Are the correct answers.
Yeah,
for this.
correct. Both are correct approximations because it means it doesn't. If you have a large beam width, the solid beam doesn't deviate that much using that. Okay, so it's only fractional changes.
So both the answers are in the given range for this answer.
Yeah, yeah.
Okay, sir.
Because both are the right approximations only. Okay.
Okay, sir. Well, now I have given omega square. Sorry, omega is equal to theta square. So do I have to change it? Oh no, that's why I'm asking.
It's up to you.
Okay.
Okay. So what is your range coming out to be?
Pi square is the answer that I'm getting. Pi square is the radian. 9.8696 is the radian.
Which one?
For the last question, 10 ones.
Week which? Week
Week 10.
week 10. So you are getting
Pi square.
pi square.
9.8696. It's the radians.
How come?
Because here u is cos theta into 1 plus secant theta, and u max is when both secant theta or cos theta is 0 degree. So that is one more. When they are 1, that is theta is equal to 0. So the maximum value will be 2. So half of the maximum value will be 1. So cos theta into 1 plus secant theta will be 1. So cos theta plus secant theta into cos theta is equal to 1. Since secant theta into cos theta is actually 1, both the ones will cancel and we'll get cos theta equal to 0 and theta is pi by 2.
Wait. Theta comes around 2 pi by 3.
2 pi by 3.
Yeah.
How
See,
the-
you have to just equate it with 0.5. You don't have to go to that much of trouble.
but the maximum value of this given
See,
function is
equation will
2.
become 0.5 equal to cos theta plus 1 or minus 0.5 is equals to cos theta. So theta will come around 2 pi by 3.
No, but the maximum value of u will be when both cos theta and secant theta are 1, which means 2 is the maximum value.
No. It won't will be 2. Maximum value of u is 1. That is for what theta?
Theta equal to 0 degrees.
No.
Is when-
That's not always true. Okay.
Okay.
So means this I am saying this is not there is instead of normalized radiation intensity I should mention because this is not normalized. So the entire term, the cos theta by 2 term will be there. Okay, to make it a normalized intensity radiation.
Oh, this is, but here it's given normalized.
Okay. I got the issue. So take it as normalized and equate it 0.5. I think the problem is with the forming the question. Okay.
So it's not 1, so it's 0.5. So the maximum value you are saying is 1.
1.
And the theta will be 2 pi by 3, which on multiplying with 2 gives the half power beam with us 4 pi by 3.
Correct.
Okay. Okay, sir.
So, sir, we just have to equate u with half, sir.
Yeah. If
Okay, sir.
see, even if the question is wrong, if you just see whether what is it is given, if it's normalized radiation intensity, then equate it with 0.5 blindly, even if it's not normalized. So what happens sometimes while forming equations, we kind of skip those things. It's like it means kind of skips away from our mind. If it is normalized mention, equate it 0.5, you will get the answer we are expecting. Okay.
So in these types of questions, we need to blindly equal it to 0.5.
Correct. Because it's already mentioned normalized, so you consider that as normalized and equate it to 0.5. Okay.
Where if it's not mentioned normalized, are we supposed to find the maximum value of this function?
Yeah. Correct. If it's not mentioned normalized radiation intensity, that means you have to find the maximum value and then normalize it and then equate it to 0.5.
Okay. So, but in either case, even if this function is not normalized, its maximum value will be 2. So dividing it by 2 will be 1. So the half of it will be 0.5 again. That is, if the maximum value will be 2, and on normalizing it, the function will yield 0.5 as the maximum value. Is it correct, sir?
Correct.
Okay. Thank you, sir.
Okay. So I think time is up. We will again meet tomorrow and cover the other half of the the revision, and then sir will take few concept studies and all. Sir will take few clear few doubts and concepts. Okay. So thanks all.
Sir, will you share the slides, sir?
Yeah, sure. We will share everything.
Yes, and sir, one thing, sir. Whenever sir is taking the class, sir, I am getting a meeting, YouTube live stream link through SMS, sir. But whenever you are taking the class, I am not getting any such thing, sir.
Pardon?
Sir, whenever Abhirup sir is taking the classes, the live classes, sir. So via SMS, I get a link from NPTEL for a YouTube live stream, sir, which I can check later also for the entire session. But
Okay,
whenever you are taking the session, I'm not getting any such link, sir.
So, okay, I will check with the NPTEL. What is the issue? Okay. So,
yeah, sir.
Solve it. Okay.
Yeah, sir.
Okay.
Thank you, sir.
Thank you.